Hi, in this video we will introduce orthogonally diagonalizable matrices and we will study some examples of 2 by 2 matrices to check if they are orthogonally diagonalizable or not. Well, let me start by recalling that we call them matrix, so an n by n matrix, square matrix, is called diagonalizable if we can find an invertible matrix P such that P inverse AP is a diagonal matrix. In other words, P diagonalizes A. Well, P is invertible and D is diagonal. So this was the notion that we worked with, and remember the condition was that all eigenvalues have same algebraic and geometric multiplicities. But now we want to ask for more. We not only want P to be invertible, we also want P to be orthogonal. Can we find such P that is not only invertible but orthogonal matrix? By orthogonal, you know that we mean that the inverse is the transpose of that matrix. So we are looking for those matrices that can be diagonalized by an orthogonal matrix. So that is the definition of orthogonally diagonalizable matrix. An n by n matrix is called orthogonally diagonalizable if we can diagonalize A using an orthogonal matrix where Q is an orthogonal matrix and a D is a diagonal one. So orthogonally diagonalizable matrices are a special case of just diagonalizable matrices. Well, let's see in some examples. In 2 by 2 matrices, we can check this condition easily because of very interesting fact that we know about the inverse of how to find inverse of a 2 by 2 matrix. Let's start with the first one. Is this orthogonally diagonalizable? Well, A is actually diagonal. So when A is diagonal, you can write A as A inverse AI equals to A itself. In other words, the matrix, the invertible matrix is identity matrix, and the diagonal matrix is matrix itself. D is A. But if you look at this I inverse is the inverse of identity matrixes itself. And we know that the transpose of the identity matrix is also itself. So in other words, we have already found not only identity matrix is an invertible matrix, but also it is an orthogonal matrix. So this is in general true that every diagonal matrix is orthogonally diagonalizable. That's nice. How about this one? Well, here, remember we always start with finding eigenvalues. In this case, this matrix has only one eigenvalue, 2. The span of the eigenspace of this matrix, this eigenvalue, so E2, is actually span of just the matrix 1, 0. Well, right away you notice that eigenvalue lambda equal to 2 has algebraic multiplicity 2, so algebraic multi is 2, but geometric one, E2 is only one dimensional, so the geometric multiplicity is 1. And from that you can conclude that this is not, A is not diagonalizable. Let it alone to be orthogonally diagonalizable. Because orthogonally diagonalizable is a special case of diagonalizable. If something is not diagonalizable, it's not going to be orthogonally diagonalizable. Very nice. The third example is an interesting example. Here we have two eigenvalues. Lambda is 0, lambda is 2. And it's very easy to check that E0 is span of 1, 0, and E2 is span of 1, 2. And right away from there, you can conclude that A is diagonalizable. Yes. And remember, how did we find the invertible matrix in that case? In that case, we find a basis for E0, for E2, put them as columns of a matrix that will form the invertible matrix. A basis for E0 is not only 1, 0 is a basis, you can multiply that by any constant you like, but that constant must be non-zero. And a basis for E2 can be any multiple of 1, 2, but we have to make sure that that is also non-zero. So this diagonalizes A, definitely. For any C non-zero and D non-zero, this diagonalizes A. Well, now the question is that, can we find values of C and D such that this matrix is orthogonal, or is there values of, or are there values of C and D where P is orthogonal? In other words, orthogonal means that P inverse is equal to P transpose. And while being 2 by 2, I know how to find the inverse. It is 1 over determinant. Determinant here is 2CD times, swap the entries on the main diagonal. So this is 2DC, 0 off diagonal entries multiplied by -1. Well, if I multiply this inside, I will get 1 over C, -1 over 2C, 0, and 1 over 2D. Yeah? This is A inverse, but when A inverse is the transpose of P itself, well, the transpose is always easy to find. Just switch the rows and columns of the matrix. So this is the question. Are there values of C and D such that these two guys are equal? But if you look at this thing, right away you notice that, well, this means that D must be 0, but we assume that D is non-zero. This is a contradiction. Or you could have looked at this, guys. 1 negative 1 over 2c cannot be equal to 0. That number is always non-zero. Okay, so that's another contradiction. So that means that, are there any such value? The answer is no. So we can conclude that A is diagonalizable. We already saw that. But not orthogonally diagonalizable. So there are matrices which are diagonalizable, but they are not orthogonally diagonalizable. Okay, another example. Well, lambda, here we have two eigenvalues, lambda 0 and lambda 2. Eigenspace of 0 is span of 1 and negative 1, and eigenspace of E2 is span, eigenspace of 2 is span of 1, 1. Okay? Well, and right away from this, you can conclude that yes, A is diagonalizable. And, well, if you're looking for the invertible matrix, in this case, you put any multiple of that, C, negative C, well, C must be non-zero, and any multiple of this guy, D, D. This guy will diagonalize A. Now, the question is that, is there value matrix P which is of this form and orthogonal? Or in other words, are there values of A, C, and D? So are they values of C and D which makes P? We already know it is invertible, but are there values that P makes P orthogonal? So that is the answer question we are looking for an answer for. So here I assume that D is also non-zero, otherwise the matrix is not invertible. Well, orthogonal means what? P inverse is equal to P transpose, inverse of 2 by 2 matrix. The reason that we can check this thing is that inverse of 2 by 2 matrices are easy to find. So in this case, we will have 2CD over, change the entries on the main diagonal, multiply off diagonal entries by negative sign. So this will be 1 over 2C, negative 1 over 2C, and 1 over 2D, 1 over 2D. So that's the inverse. Is this equal to the transpose of the matrix P? Well, transpose means that you swap the entry rows and columns, yes? So this will be the transpose. Well, let's see if that can be equal. Well, the first row, the only condition you need to have is this must be equal to that. 1 over 2C equals to C. The second entry of the first row will give you the same condition. And we are looking for 1 over 2D must be equal to D from the second row. Well, solve this thing. So this means that C2 is equal to 1 over 2, and that means that C is plus or minus 1 over root 2. From this, we need to see that D2 is equal to 1 over 2, and then D is plus or minus root 2. Well, yes, the answer is yes. You can find values of C and D. You pick any of the numbers you have here, such that the matrix, the invertible matrix P, is orthogonal matrix. And for example, if I take both of them positive, this will be an orthogonal matrix which diagonalizes, so this diagonalizes this matrix A. And yes, A is orthogonally diagonalizable. Well, these conditions are not easy to check for n by n matrices. Well, if you do it the way I did, but we will learn there is a nice fact, there's a nice theorem that makes life very easy for us. And checking if a matrix is orthogonally diagonalizable is going to be very easy.